Hey class, today we're going to do a short recap on our lesson we had previous, and then we're going to lead into what we're talking about today. So let's go ahead and start our recap. If you remember from the last lesson, we talked about how light consists of electromagnetic waves, and these waves include a lot of different kinds like radio waves, microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. And then we also talked about how the only rays we can actually see are visible light. So here we had our electromagnetic spectrum, and of course the only one that we can see is red through purple of this visible light range. Then we talked about, well, what happens when we take light and we pass it through a prism, or a machine called a spectroscope. We can see that our light actually separates into this spectrum of colors that we recognize as colors of the rainbow. And we talked about how if it was white light, it was going to produce a continuous spectrum. But if the light was powered by, let's say, an element, that element made a specific lines within our continuous spectrum. Instead of it being a continuous rainbow, we just saw specific lines here. And we called those the atomic emission spectrum. For example, we talked about helium lamp producing these discrete lines. And we talked about how no two elements have the same discrete atomic emission spectrum. So sodium's atomic emission spectrum looks different than hydrogen's. And of course, hydrogen's looks different than, right here, calcium's, because they're all different. But what we're going to hit on today is what actually causes an atomic emission spectra that we see for each element. The key question to answer that is when atoms absorb energy, it causes their electrons to move to a higher energy level. But these electrons can't stay at that high energy level forever, so they're going to eventually lose that energy that they gained, and the way they release that energy is they release it in the form of light when they return to lower energy levels. And I'm going to go ahead and star this because honestly, this is a very important part of this lesson. So when an electron is at its lowest possible energy, we like to call this its ground state. It's its most stable state, so that's something to know. Again, usually it's its most stable state. And in a ground state, the principal quantum number is 1, because that's our lowest energy, it's our most stable. However, electrons can move to a different energy level by absorbing energy, and it can raise it into something called an excited state. So for example, an electron can move from energy level 1 to 2. It can move from 1 to 3, 1 to 4, depending on how much energy it absorbs. So again, here, the excited state, we should know that this is less stable. And this cannot stay forever. Eventually, it's going to have to release that energy it absorbs. So how exactly are we getting light from this? Well, the frequencies of light that is emitted when an atom or an electron within an atom lowers an energy level is going to be related to our frequencies. So light emitted by an electron moving from a higher to a lower energy level, its frequency is directly proportional to the energy change that that electron releases. So again, key point here, frequency is directly proportional to energy changes. And in fact, a German physicist named Max Planck actually showed this direct proportional mathematically by saying that E, as in energy, is equal to H, which is going to be, we're talking about as a constant, and then times V, which we learned that V was frequency. So if we, again, we look at this, E is energy, and energy's SI unit is actually joules. So it says joule, J is the joule, the SI unit of energy. So we should be using J for this. H, it says up here, is a constant. That means its value will never change. It is always going to be the same value, which is 6.626 times 10 to the negative 34th. This actually is sometimes called Planck's constant. And then V, we already learned that V was frequency, and its unit that we use for it is hertz. So our first problem says, what is the energy of a photon of microwave radiation with the frequency of 3.2 times 10 to the 11th per second? Per second is just another way to say hertz, by the way. So here, again, we're going to be using the equation E equals HV. So here it's saying what is the energy, so I'm going to plug in X for E because I don't know that energy. This is going to equal out, and we need to do H. Now remember, H is a constant. H will always be our this value right here. It will never change. So we're going to go ahead and plug in that value, 6.626 times 10 to the negative 34th. And then it tells me my V, my frequency. It says my frequency is 3.2 times 10 to the 11th. Just like what we did the other day, we want to make sure that both of these values are in parentheses. So again, you're going to put parentheses where you see them here written, and we're going to be multiplying these two values together. When you actually do that, we actually get 2.12 times 10 to the negative 22nd. And since it's asking for energy, we want to make sure that we put the unit for energy, and the unit for energy is a joule. Our second problem is a little bit different. Instead of finding energy, it wants us to find what is the frequency of a photon whose energy is 1.166 times 10 to the negative 17th joules. So again, remember our equation is E equals HV. We know our energy because that's what it actually gives us. So we're going to plug in 1.166 times 10 to the negative 17th equals, remember our H value is a constant. Our H value will never change. Remember, this is Planck's constant. It's always going to be this value. So we're going to plug in 6.626 times 10 to the negative 34th. And then our V, we don't know that. That's what we're trying to find. So we're going to plug in X for that because we don't know that frequency. From here, we want to get X by itself. So to get X by itself, I'm actually going to divide by 6.626 times 10 to the negative 34th to get X by itself. And that means X would equal 1.7597 times 10 to the 16th. Now it's asking for frequency, so we want to make sure that we put the unit for frequency, which is hertz. Couple things before I finish out this lesson. Your homework is actually going to involve a little bit of a combination between what we've learned today and what we did a couple days ago. So let's remember that our equation we learned a couple days ago was C equals wavelength times frequency. So again, remember C is speed of light. It is a constant, so remember our speed of light is 2.998 times 10 to the 8th. This is wavelength, which is given in meters. And then V, remember, is frequency, which is going to be given in hertz. A couple of things that I want us to recognize between both these equations is that both of these equations has frequency as part of it. I have V as frequency here and V as frequency here. So if I was given wavelength, so let's say given wavelength, we want to first use C equals wavelength times frequency. So, and trying to find energy, we want to first use the equation C equals lambda times V and find frequency. And then we're going to plug frequency into into our energy equation. So again, if we were given wavelength and trying to find energy, we're going to have to first use one equation to find frequency, which is this V, and then we're going to plug what we found for frequency into our energy equation. Last but not least, a couple other things I want to talk about is up here, this is a hydrogen spectrum. There are 3 groups of lines that correspond to how much energy is lost whenever an electron loses energy. So you're going to notice on my slide, not necessarily on yours, that the bigger the leap, the different the amount of energy that we have, and the different you will see the colors. So notice that here I have a big drop in energy, and notice my color is more in the ultraviolet range. So we can't really see ultraviolet. Here is our visible range. Notice here I have a bigger drop. I see purple. Here it's like a middle drop. I see more blue. And then here I don't have as big of a drop, so I see red. So we see these different colors based on how much energy is dropped. So less energy, I see red. Here I have purple, which has more energy. So I'm actually going to go back up to this picture to show you again, and I'm going to go ahead and star this. Red tends to have low energy, and purple has high energy. So again, if we see the color red, it's not giving off that much energy, but if we see the color blue, we're giving off high energy. And again, that goes to what we know about frequency. Remember, we said over here we had low frequency, and over here we had high frequency. So you're going to see that these are both directly related to each other. As frequency goes up, so does the energy. So another thing to also point out is, again, the bigger the jump, the more energy it gives off. So if I asked you, in a hydrogen spectrum, which of the following transition produces the spectral lines of the greatest energy? And it says 2 to 1, 3 to 2, or 4 to 3. You're going to look to see who is the biggest jump. So again, from 2 to 1, 3 to 2, 4 to 3, 5 to 4. Notice, like we talked about in section 1, the farther we get out, the less those rings are spaced apart. And so when I ask you which one has the greatest energy, we should recognize that a 2 to 1 is a bigger jump to have the greatest energy. So again, the jump 2 to 1 is a bigger gap than 3 to 2. Now, if I said 7 to 1, that's a bigger gap, so technically that would be more energy. So we want to look at the gap size to figure out the answer. So in other words, I'm going to make a little mark here that you can mark on your notes. We want to find the biggest gap jump. Last but not least, the glass tubes and lighted signs contain helium, neon, argon, krypton, xenon gas, or a mixture of these gases. And the reason we use a bunch of different gases to produce colors in a neon sign is because each gas, each element produces its own color because of its atomic emission spectrum. So when we excite it and it releases that energy in the form of light, it's releasing different amounts of energy. And so we see these different colors, which is super cool. And that's the end of today's lesson. If you guys have any questions, please make sure you ask, and I hope you guys have a great day.